So elimination is our theme, so we're into our third reaction type. For your diploma, they're only going to use the word elimination. Now, I like to teach it and use the two types of elimination. Okay? One type removes water. Okay? The other type removes hydrogen and a halogen. And they happen differently, and they have different reactants and reaction conditions. Okay? But again, both of these you can just call elimination when you're asked what category of reaction occurred. So with dehydration, you'd be looking for alcohols. Okay? Now you're going to see a little bit more of the reaction condition shortly. Alcohols can remove an H and an OH, so that together would be a water. In the dehydrohalogenation, you're going to have an organic halide, and you're going to get H and an X, where X is a halogen. So you might get HCl or HBr. In either case, whether you remove water or you remove H and a halogen, you're going to get a double bond where you remove them. So you're going to get an ene as a product. So let's take a look at dehydrations first. So in order for a dehydration reaction to occur, you don't need another reactant, but you need a catalyst. You need an acid catalyst. Now in chemistry, we put catalysts above or below arrows. They're not a reactant, they don't get consumed. So if you started with a pH of 2, you would finish at a pH of 2. The acid would be used up and regenerated. Okay? But you're going to see me use the H plus acid in this reaction. Okay. I'm going to go through a bit of the why. You don't need to know the why, but for many of you, understanding and remembering or memorizing what happens can help with the why. I also like to do the why because this is a university preparatory course, and I'm going to use some language you might see in university chemistry. Okay, I'll highlight those terms that are university terms. Okay. So what the acid is going to do is attack the lone pair on the hydroxyl group. Oxygen in group 6 has 2 lone pairs and forms 2 bonds. That's Chem 20 bonding. Okay. So a H plus from the catalyst can attack those electrons, or the electrons can attack the H plus, and this makes something in university, not high school, that we call a leaving group. Okay. Again, that's not Chem 30 speak, but it's sort of trying to help you understand what happens. Okay. So an H2O, a water can come off. That's that water product you get that you have to know. Okay. Once that water leaves, you can get a double bond to form to the right of the carbon that had the hydroxyl group, or you can get a double bond to form to the left. We have to consider both ways. There's 2 possible names. Okay. When the red double bond forms, we'd lose an H. If the blue version happened, we'd lose an H on the blue side. And that's going to replace the H plus from the acid. So if we get a double bond to the left, the blue, that H would leave. If we get a double bond to the right, that H would leave. Okay. So let's do the red version first. So the key thing is find your hydroxyl group, realize that's going to leave. There's the carbon connected to the hydroxyl group. I'll do the version to the right first. So we had 1, 2, 3, 4 carbons. There's the first. There's the second that had the hydroxyl group attached to it, and I'm going to the right of the carbon that had the hydroxyl group. We're also going to lose that red circled H, and everything else stays. So we've eliminated an OH and an H. Now I have to be careful when I draw to make sure I have 4 bonds in all the carbons. Okay. So we get a water and we get butene for the red version. If we get to the left, which is the blue version, we still have 4 carbons. Okay. There's the carbon that had the hydroxyl group, and now we're going to the left with our double. And the blue circled H would also come off, and that would replace the H plus from the acid. Now we would also get a water when we make the second product. So we have all our products. We could make a butene, we can make a butanene, both would produce a water. We'd get 2 waters in total. So to complete the balancing, we'd have to have 2 of the original butane 2-ols. Okay. So all the labeling I did at the beginning, the leaving group, drawing the red arrow, drawing the blue arrow, you don't have to do any of that on assessments. But you do have to realize you could get a double bond to the right of the hydroxyl group or the left. Now you got to make sure they're not the same structure. If you do a double bond to the left and the right, and you get the same name, then you only write one of the products. Okay. So if you had an alcohol on a 2 carbon long molecule, you wouldn't get 2 names, you just get 1. You'd end up with just ethene. Okay. So this is one of our elimination types, elimination of water, dehydration. Our second type is dehydrohalogenation. We're going to get H in a halogen. Okay. We've got a chlorine atom in this organic halide. We're going to get an H and a Cl coming off. So I have a 4 carbon long or organic hydrocarbon derivative because it's not just C and H. We're going to get the same type of chemistry. We're going to get that chlorine leaving, kind of like how the hydroxyl left. But it needs different conditions to leave. We need something to tug off a hydrogen, which will help the Cl leave and form the double bond. We actually have basic conditions. You need hydroxide, but not as a catalyst. It's a reactant. We're going to use up hydroxide. So this is why I put the eliminations in 2 separate categories. You need to think of them separately because one has an acid catalyst, one has a hydroxide reactant. So we're going to get the same type of reaction. Okay. We're going to get a double bond formed to the right, and we could potentially get a double bond formed to the left. Okay. The double bond forms to the right. The hydroxide will help pull off an H on the right-hand side. If we get a double bond to the left, the hydroxide will help pull off an H to the left to form the double bond. So let's do the green version first. It's going to look fairly similar to our previous example. 4 carbons. The green double bond formation would be the second carbon-carbon bond. The very first carbon still has its 3 H's. Second carbon still has the 1 in the bottom. The third carbon still has the bottom one, but the top one got pulled off. The last carbon has all 3. Now, where you might make mistakes is what's left over. We had the Cl come off. That's going to come off as a chloride ion. Okay. And the hydroxide is going to pull off an H. So what would an H and hydroxide make? H2O, and that's a water. Now we're not quite done. We did the green version. The red version, we're now putting the double bond in the very first position. And I need to be careful, 4 bonds on all the carbons. So this will also have a Cl leave, but it'll be chloride, and you'd get a water. So an H and a Cl come off, but they don't end up together. The H ends up with the hydroxide in a water. The halogen ends up as an ion by itself. We've got 2 different products, but1-ene and but2-ene, the 1-ene on the bottom, the 2-ene on the top. So we need 2 organic compounds to do this. And that's our dehydrohalogenation, but on the diploma, you'll also just call this elimination. You will not see dehydration and dehydrohalogenation there. Last little bit, I'm just going to add a spectator ion in that you might see, and hopefully it doesn't confuse you. Okay. On a workbook question, a test or diploma question, you might see the hydroxide as sodium hydroxide. Okay. The sodium isn't going to do anything. Okay. If you have sodium hydroxide, okay, the sodium would just show up paired with our negative ion at the ending, but it's a spectator. Okay, it's not going to do anything. Okay, you could balance it without showing the sodium, okay? But you can't buy a bottle of hydroxide ions. So the reactant for this hydroxide, you could use sodium hydroxide, lithium hydroxide. Okay? It doesn't matter what you use. The metal ion, in this case sodium, is a spectator ion. The only thing I should have done is this hydroxide would have also needed 2 units. When I went and doubled the organic compound, I should have put a 2 there. So now this is balanced with a spectator ion. Okay. Again, you have to be able to handle with a spectator or without. So that's mostly through our reactions. We have seen addition, we've seen substitution, we've seen dehydration, we've seen dehydrohalogenation. Now just a quick recap of some previous reactions that you might see. Complete combustion and using generic formulas. Okay. I'm going to write a balanced chemical equation for the combustion of 2,2-dimethyldecaine, and I'm not going to draw it. We've learned skills that would replace drawing that to get the molecular formula. Combustion is a hydrocarbon, C's and H's. We're going to have to figure out that count, but a hydrocarbon, a fuel plus oxygen, which is a gas under standard ambient conditions, is going to make carbon dioxide. And if it's open combustion, we'll get water vapor. Now that's a specific outcome of the thermodynamics section that you know you get water vapor under open combustion. So what is that fuel? We can't balance this without knowing our fuel ratio, our hydrogen-carbon ratio or coefficients. Well, we can get the carbon count. Dec is how many carbons. That's our last prefix. That's our 10. We have 2 methyls. How many carbons in a methyl? Just 1, but there's 2 of them. So we've got 10 in the stem, we've got 2 in the branches, so this is a C12. I could draw this, but it's a total waste of time. I can predict the hydrogen count knowing it's an ane. So what was that? We had 2n plus 2, 2n, and 2n minus 2. The anes are the 2n's plus 2. So double the carbon and add 2 because the 2 n's have an extra H. So 12 doubled is 24, plus 2 is 26. So no reason to draw this. In theory, on an exam, I could put, you know, a ane that has 100 carbons and ask you to burn it. Okay? And you wouldn't draw out that 100 carbon ane, you would just double the 100 plus 2. So now this is just science 10 balancing. Okay? Now I'm going to make the same comment that I'd make in science 10 to help balance combustions quickly. The hydrogen is going to end up in pairs, and we need an even number of pairs so that we get an even number of oxygen from the water, because our oxygen has to be in pairs or even. So we've got 26 hydrogen. That would be 13 pairs, right? And that's going to give us an odd number of O's, and it's going to get us into a bit of a loop or trouble. Whenever you see that odd number coming, if you double the fuel, you're going to have an even number, and it's going to balance really nicely. So this is just a strategy or a shortcut to help balance combustion and preventing getting an odd number of O's that will cause trouble. Now I have 2 times 26, okay, which can give me 26 pairs of hydrogen, or 26 waters. Okay? And now I have an even number, and everything's going to balance nicely. Okay? I have 2 times 12, or 24 carbon. So I'm going to get 24 carbon dioxides. And then for oxygen on the product side, I have 48 in the carbon dioxide, oxygen. So 24 times 2, and then I've got 26 more oxygen from my water. So that's 74. Okay. And 74 is divisible by 2. How many pairs make 74? It's 37. Okay. If we hadn't have done that doubling, we would have got a fractional answer for the oxygen. We would have got 37 over 2. Okay. So the ultimate point of this, remind you of combustion, oxygen, CO2, and water vapor, and using generic formulas to go from names to the molecular formula. Okay. Last, just recapping incomplete combustion, so it's fresh. We're not going to be balancing incomplete combustion. I have seen environmental type questions show up on diplomas, so you need to be aware of the products. So when you have a lack of oxygen, O2 is a limiting reagent. You won't get to fill every carbon full of 2 O's. Some of the carbon that you burn will saturate with oxygen, fill up with oxygen, okay? And you'll get CO2, and that's a greenhouse gas. Because oxygen is a limiting reagent, you'll also get some carbon that only gets 1 O, carbon monoxide, which is a toxic gas. You can't see it, you can't taste it, you can't smell it, but it binds to hemoglobin in your blood and never unbinds, and you suffocate to death. And hopefully you have a working carbon monoxide detector in your house, particularly close to your furnace. Okay. You can also get carbon that has no oxygen attached to it. We saw this in thermodynamics. Okay? You do any type of combustion lab and you get some black soot. Okay? This is also very bad to breathe in. Okay? If you burn a lot of carbon, maybe in power production, and it hangs over your city, okay, you're going to have very bad air quality. Okay? It's going to be, you know, you don't want to breathe in soot. Okay? It's a problem in some cities around the world, in China, Mexico City, Los Angeles, more so in the past. Your last product is just water vapor. So that's not an environmental concern. So that's the combustion. So that's it for writing for this lesson. I'm just going to end with some optional slides you may want to go and fill in and make some nice summaries. So I've laid out a structure to make yourself a review guide. I've listed out all the families, ane, ene, ine. We got aromatics. I didn't put the cyclos in. Organic halides, alcohols, carboxylic acids, and then we'll do esters shortly. So you'd have a blank in this guide right now, talking about what makes that family, what is the characteristic or the functional group of that family. You could fill in an example and then name that example. Okay? Really nice for your organic unit test and a nice review for your diploma exam for studying. Okay? I've set up another type of review for you to fill in if you want for the reactions. Again, we'll have a few blanks. So to do a little summary, okay? Summarize how many products you might get. Okay? For addition, it's either 1 or 2. Okay? If something's symmetric, like a symmetric diatomic, you only ever get 1 product, and then you could do an example. So addition that's symmetric, addition that's asymmetric, addition that we haven't done yet between a carboxylate and an alcohol that makes a smelly ester. So that would be blank right now. We've done elimination of water, and we've done elimination of an H and a halogen. And at the bottom, we've done substitution. Okay. So these, again, are really nice reviews to fill in for both your test and your diploma. You can summarize 80% of this unit in these 2 nice reviews. Okay. There just isn't things like boiling points, fractional distillation, isomers wouldn't be here. Okay. So we're almost done organic.